Let us look at one example. Let's look at this example. We have signal 1 is equals to V1t. We have 5 sine 2 pi times 50t plus 90 degree. And we have signal 2 V2t is equals to 5 sine 2 pi times 50t plus 30 degree. Now the question is 1. Find the period of the signal V1t and signal V2t. 2. Find the phase difference between V1t and the V2t. And 3. You plot the waveform for the V1t and V2t. And these are the questions you need to solve. For question 1, we say find the period. And we have the frequency 1, which is the frequency for the first signal, is 50 Hertz. That's from the signal where we have V1t is equals to the amplitude sine 2 pi the frequency times the time plus 90 degree. And this frequency is corresponding to the 50. And we have the F2, which is also 50 Hertz, so they have the same frequency. Now to find the period, we know that the period for the signal 1, which can be 1 over frequency 1, so it's 1 over 50 Hertz, which is 1 cycle over the frequency which is 50 Hertz. So you have 1 divided by 50, which will give you 0.02 seconds. And for period 2, we have 1 on F2, which is also 1 on 50, which will give us 0.02 seconds. Now this is the period for the V1t and V2t. And the second question, it says find the phase difference. So for this phase difference, we have the theta 1 minus theta 2. And we all know that theta 1 is 90 degree and theta 2 is 30 degrees. Now we should have the phase difference of 60 degree. From this phase difference, we can compute that signal 1 leads signal 2 by 60 degree. This now will lead us to plotting the waveform. And from the waveform, we can see that the signal 1, which will lead the signal 2 by a phase difference of 60 degree. Now let us plot the waveform. Now we can have for V1t and time, and also the other plot for the V2t, and we can have minus 5, 5, minus 5, and 5. And this can be pi on 2, pi on 2, and this will be pi, 2 pi on 3, 2 pi on 3. We have 2 pi and 2 pi. So we can now be able to plot with respect to the waveform diagram. And we can have minus pi on 2 Now we can see V1t is shifted by 90 degree. So the waveform should be, we should have this signal coming like this. And this waveform represent V1t is equals to 5 sine 2 pi times 50t plus 90 degree. And we previously said the V1t can also be equals to 5 cosine 2 pi times the 50t. And this region represent the waveform of the cosine signal. For the V2t, we know that if this is 90, we can have 60 and 30. We can have 30, 60, and minus pi on 2 in this region. We can have this portion and this portion. And we can see the signal is shifted by a 30 degree. So we can start from minus 30. If we take the difference of minus 30 all the way to will be 330 degree. If we are to take a difference between this region, we should end up with 2 pi or 360 degree. To prove, we can say 330 degree minus 30 degree. We now should have 360 degrees, which now represent the full cycle of a waveform. And we know that our signal, which is shifted by 30 degree, must be within this plane. Similar for this case here. In order to have a full cycle, we have, which is here, begin from here and it will end in this portion here. And we have 270 degree minus 90 degree, which will give us 360 degrees, which is a full cycle of the sine signal. So if we begin at this point, we know that this is 30, 60, and 90. So this region, we will have the peak of our signal, and we have another 90. We can have 3, 6, 9. So in this region, we will have another peak, and we should have 3, 6, 9, and this will be another sample, and we can have 3, 6, and 9. So it will end in this region. So this is our plot for the signal. Now if we want to create the waveform, we should have something like this. And this is now our V2t, which is equivalent to 5 sine 2 pi times 50t plus 30 degree. And we said that V1t leads the V2t by 60 degree. And we can see that from this region, and we can have 1 and 2. So it is leading, and this region is now the 60 degree phase shift. And we can see that from here to here is 30, from here to here is 60. So it is proven that the V1t leads the V2t by 60 degree. And we can prove that from this region to this region is one cycle, and from this to this we have the one cycle. The only thing which is different from the two is the way they shift. The first signal is shifted by a 90 degrees, and the second sine signal is shifted by a 30 degrees. So given any question along this manner, you now can be able to compare by finding the period between the waves. You find the phase difference between the wave. They may have different amplitude, but the important difference is that we are trying to understand how the signal is shifted. and this shift is known as the phase of the signal, and you can be able to plot the waveform with respect to the shift. So with this example, I believe you should be able to fully understand what is a signal and the phase shift. And also the important thing to remember is that the phase shift of a signal normally shifted in the horizontal axis, which is the x-axis of the graph. Different type of electrical circuit normally deals with each of these parameters. For example, in our video, we talk about the amplifier. The amplifier does not deal with the parameter of the signal such as the phase. However, the amplifier deals with the amplitude of the AC signal. When we talk about which type of component in an electrical circuit will affect the phase shift, we all know a component known as a resistor and inductor. We will see how capacitor and inductor normally affect the phase of the signal. In this case, we will look at a resistive circuit. And we know from a resistive circuit, if we have the AC into a circuit and we have the resistor load, we have the voltage, and we have the current flowing through a circuit. And we all know that the Vt is equals to the amplitude sine 2 pi ft plus the theta. And also we have It, which is equals to I peak sine 2 pi ft plus theta. In a resistive circuit, we can see that the voltage and the current both are in phase, because the resistor load in a circuit will decrease the current flow in a circuit. If we are to describe in terms of the waveform, we have the waveform given that pi on 2, let's say pi, 2 pi on 3, and we have the 2 pi. We can say the max amplitude and the mean amplitude. And we can draw this waveform represent the Vt, and we can have the purple, which represent the It. When we increase this resistor load, the only thing that will happen is that we will decrease the amplitude of the current in an electrical circuit. However, from this waveform, we can see that both are in phase. The voltage and the current are in phase in an resistive circuit that deals with the AC signal. And if we decrease the resistance closer to zero, that means the current and the voltage amplitude will be in phase and with the magnitude. And now we will look at the inductive circuit. In an inductive circuit, we have the AC connected to the inductor. Inductor is nothing but an electrical circuit that normally stores energy in the form of the magnetic field. And we have the inductor, and we have the voltage AC and the current through the inductor. Now we can see that using the same equation given, like in the first equation for the Vt, we can simply say Vp sine 2 pi ft plus 0. There is no phase shift. And for the current, Ip sine 2 pi ft plus 0 degree. And the waveform for this inductive circuit can be given as the max amplitude and we can have the mean amplitude, and we can have pi on 2, we can have pi, 2 pi on 3, and 2 pi. And the voltage, we can see that this represents the Vt. However, for the current, and this now represent our It, and we can draw the conclusion that the current It now lags behind the Vt, and the phase difference between the two is the 90 degree. So when we say that the current is lag, that means if we are to draw up the equation, we can see It is equals to the voltage max of a signal divided by the angular frequency times the inductor value sine 2 pi f t minus 90 degree. So with this 90 degree, we all know that the current shift towards the right. In this case, when we are to see the point of origin, the point of origin is this point here. So we can see now that the current waveform It is shifted towards the right, and it begins in this point. Now we know that the current lags behind the voltage. To make it more clear, this graph, if we are to say this is the starting point of the Vt, now what will happen to the current? And if this is pi on 2, we now will have a current which begin in this region and hence in this region. So the phase shift is 90 degree, and you can see from this region is also 90 degree. So this represents what normally happens in an inductive circuit. That means when you connect an AC to an inductor, the current will lag behind the voltage. That's why we have the phase shift, which demonstrate how you will be able to see the waveform of a current and a voltage, because we said in the beginning that when we talk about the alternating current, we talk about the voltage is alternating as well as the current is alternating. If you enjoy watching our video, you can click the subscribe button and share this video with your friends so they can also learn what is the component in an alternating signal. And for this example, we want to see the current. So in this case, the current is shifted towards the right, and when they are in phase, we know that the current It is equals to the Vmax as a mathematical representation of the circuit divided by the R times the sine 2 pi ft, which describe the current having no phase corresponding to the voltage. So the current and the voltage are in phase. However, for the inductive circuit, we know that the current It lag the voltage. And in this case, we see that the voltage and the current, they are in phase. Now we will look at a capacitive circuit as a final example. So for the capacitive circuit, we have the AC and we have a capacitor, and we have the voltage and the current. And this type of circuit is similar to what we have described in our previous example of the waveform. We can have pi on 2, pi, 2 pi on 3, and pi. T, we have the max value of the amplitude and the mean value of the amplitude. Now we can see that this is our Vt, and we know that Vt is equals to Vp sine 2 pi ft plus 0 degree. And what will happen to our IT? We can do a little bit of extension, and now we will look at the IT, which is the current through the circuit. And this now becomes our IT. So from the circuit, we can clearly see that the current now leads the voltage by 90 degree. And we can be able to come up with equations such that the IT is equals to the angular frequency times the capacitance times the Vp sine 2 pi ft plus 90 degree. And we can see that with this 90 degree, the current is shifted towards the left. So if we add to say minus pi on 2, that means this is where the current begins. And this is the point in which the voltage begins at t is equals to 0. So when we compare with the origin for t is equals to 0, we can clearly see that the current is shifted towards the left by a 90 degrees, and it is similar to most of the example we look at previously. So I believe with such explanation we can see that by summary of the phase in an electrical circuit, for the resistive circuit we see that the voltage and the current, they are in phase. And for the inductive circuit, we can see that the current lag the voltage, and from our example it is lagging the voltage by a 90 degree or pi on 2. And for the capacitive circuit, we see that the current leads the voltage, and in this example we can see it is leading by pi on 2 or a 90 degree. So you can see in terms of the phase difference in an electrical circuit, components such as a resistor, inductor, and the capacitor, they normally handle the phase shifting of the alternating signal in an electrical circuit.